Welcome to UVU CS3060 Lecture 9.0, where we give an overview of some of the concepts of main memory. A little background first. When it comes to the programs that you write and compile, those programs, the binaries, are stored on a storage medium such as a hard drive or an SSD. That storage is not usable by the CPU directly. When a CPU needs to run an instruction, that instruction has to be in main memory to be executable. That instruction gets moved from main memory into a register. Both main memory and registers are directly addressable by the CPU, and this is an important idea. Other devices, such as hard drives or network devices, are not directly addressable. They require special instructions in order to access the data from those media. So, because the CPU can only address main memory or registers, then a program must come from a storage medium and be put into main memory before the CPU can access that program. Now, the way the CPU works with main memory is basically through two operations. One operation is the read request, where an address is put to main memory and a read request is sent. Then data is given to the CPU and put into a register. The second operation is a write request, where the address to memory and the data for that's to be written are given to the memory unit, and the write request is given. Registers, on the other hand, are just simply directly addressed and can be actually operated on in at least one CPU cycle, or sometimes even less, where you have one CPU instruction that accesses multiple registers. Main memory, on the other hand, can take many cycles, hundreds if not thousands of cycles to complete. And what this does is the CPU will have to wait while that memory request is handled by the memory unit. Because of this long length of time where the CPU really is doing nothing but waiting, we call this a stall, or a memory access stall. Now, there are ways to mitigate this. One way is to put specialized memory between main memory and the CPU, called cache. What happens is a CPU requests memory access. When that memory access happens the first time, the data in main memory actually gets moved to this faster cache, which only takes tens of CPU cycle to access. When that memory resides in the cache, the next request actually is handled by the cache, which is much, much faster than main memory. There's problems we need to deal with, as in caches are very small. So what happens when the cache fills up? What kind of replacement do we do to make sure that that cache has the most recent access to memory? We also need to be concerned with memory protections. In multiprocessing systems, we can have multiple processes running simultaneously or concurrently. Those particular processes need to have some sort of guarantee that their memory is protected from the other processes. And there needs to be some way, automatically, when a process tries to exceed its particular its memory bounds, that the operating system is notified so that that process can be dealt with appropriately. One of the ways the protection is handled is using a pair of registers called the base and limit registers. The base register identifies for each process where the process's memory starts. So in our example here, the base register contains the value 300,000, indicating the memory address where the process starts. So this is the beginning of that process's memory. The second register, the limit register, identifies how much memory this particular process has. This is not an address, but is really the number of bytes that this process is allowed to use. If you add this limit to the base, you get the end memory address for this particular process. This base and limit register set a boundary where the memory accesses for a process are allowed. Anything before this or anything after these two boundaries, is considered an illegal memory access. The way this is handled is with every memory access. This includes retrieving an instruction as well as reading and writing data. Every memory access takes the address, which is called a logical address for that particular CPU, and that logical address is first compared to the base register. That base register tells us the top of the memory range. So any address that's larger than base can be considered valid, and you can continue on to the next comparison. Any address before the value in base, would actually throw an operating system trap, allowing that operating system to manage this particular exceptional condition. If the address is greater than or equal to base, then the address is also compared to the base plus the limit, and it is checked to see if it is less than the base plus the limit. If the address is less than base and limit, then the memory access is allowed, and main memory is able to handle this. Otherwise, again, this particular memory access is invalid, and notification is sent to the operating system about that process and the illegal access. And the process is handled appropriately by the operating system. This again happens with every memory access from the CPU. Every time something happens that should go to main memory, these two checks must happen first to validate the logical address from the CPU so that it can be used physically by the memory system. This brings us to the end of Lecture 9.0, where we give an overview of main memory.